So this is about the Bohr model in the presence of the magnetic field. A little background. I'm just trying to zoom. Okay. Sorry. A little technical errors here. Issues here. Okay. A little background. The Bohr model of hydrogen is based on the assumption that electrons travel in specific shells or orbits around the nucleus. He made three famous postulates. One of them is that only those orbits are allowed for which the angular momentum of the electron is an integral multiple of the Planck's constant divided by 2 pi. I am focusing on that postulate specifically for this project. We define the angular momentum as being the Planck's constant times the number of nodes. Another phenomena explored in this project is the Zeeman effect. The Zeeman effect is the splitting of a spectral line into two or more components of slightly different frequency when the light source is placed in a magnetic field. So the hypothesis and the objective for this study, we are interested in studying the effect of the number of both integer and non-integer nodes on angular momentum. We hypothesize that the angular momentum of the orbital is expected to increase with an increase in the nodes, as shown on this schematic here. An increase in the number of nodes is expected to decrease the shift in the energy of the given state. Proving the Zeeman effect on atomic spectra, we hypothesize that there will be splitting of the spectra in the presence of a magnetic field. As shown on the schematic here, the schematic is just basically giving us a visual representation of this. So the methods utilized, a Bohr model code was provided to us by Dr. Killen and to test the hypothesis using MATLAB. A modified Hamiltonian was created by subtracting the product of magnetic field and angular momentum from the original Hamiltonian, as shown here. The relationship between the angular momentum and the nodes was observed by changing the node from 1 to 2 and then to 3, and then seeing the effect of those changes on the angular momentum. We also repeated this same thing, but with a number of nodes that are non-integer number of nodes. To test the Zeeman effect, the energy diagram with varying nodes and no magnetic field was used as our control. And then those same nodes were then used with a constant magnetic field of 0.05 Tesla to see the effect of the magnetic field on each of the systems. So our results, with increasing number of nodes from 1 to 2 to 3, we did observe an increase in the angular momentum. This is a snapshot of the movie that we will be watching sometime later, but here we use integers, and then this other one is where we use fractional values of number of nodes. We did observe an increase in angular momentum, but then the shape of the orbital looked a little bit shaky. So I'm just going to show you a video here. So this is when the node is at 1.5, and then this one is with the node at 1.9. And this is another one too, with the node at 2.5. So for the results for the Zeeman effect, we compared we have our control, which is A here, and then B. For A, there was the number of nodes was 2.5 for A, but we did not apply any magnetic field on it. And then for B, the number of nodes remained the same as 2.5, but there was an applied magnetic field of 0.05 Tesla. With no applied magnetic field, the lines are overlapped, and when a magnetic field is applied, the lines straighten. This same thing was repeated with a different node. Here, the node is at 2.7. I kept the magnetic field constant for easier comparison. And then this is what we again, the same thing as the first one. And then here, the number of nodes is 2.9. Again, with magnetic field applied, the overlapped lines were straightened. What we gathered from this is that seeing how the angular momentum kept increasing with every increase in the node, we were able to prove Bohr's third postulate. When the index or nodes are fractional, the shape of the orbital changes. This is due to the fact that the angular momentum is quantized, and only those orbits are allowed for which the angular momentum of the electron is an integral multiple of the Planck's constant divided by 2 pi. An increase in magnetic field did increase the splitting, and the lines were straightened out. The increased splitting due to the increased magnetic field is consistent with the Zeeman effect. The degenerate energy levels are raised and lowered with increased splitting occurring with increased magnetic field. So that is this one. As you can see here, this line, for example, let's take that this line, for example, it was here, and then but with an increase in the number of nodes, it just kept decreasing. The increased splitting due to the increased magnetic field is consistent with the Zeeman effect. Again, the degenerate levels are increased and lowered, like I said before. An increase in the number of nodes, decreased displacement. With the nodes at 2.5, that was what I was trying to explain here. The furthest displacement was up there, and then it just kept decreasing with an increase in the number of nodes. So conclusively, the angular momentum of an atom increases with an increase in the number of integral nodes. The shape of the orbital deviates from normal when the nodes are non-integral. This is in concordance with the quantization of angular momentum. Added magnetic field induces splitting of the atomic spectra. As the number of nodes increases, the angular momentum also increases. And because the product of the angular momentum and the magnetic field is subtracted from the Hamiltonian, a larger value of angular momentum leads to a drop in displacement. Questions?
Okay, please join me thanking my SSI.